In this video, we solved problem 8.4.027, point MI from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate the indefinite integral and use capital C for the constant of integration. And this is our integral. Now, another clue for how to approach this problem comes from the fact that this is from section 8.4 in the Larson and Edwards text. And that section is about trigonometric substitution. Now remember, we said that if the integrand involves an a squared plus x squared, or we could just as easily call that a squared plus u squared, use a certain type of substitution, or a squared minus u squared, you would use a certain type of substitution, and u squared minus a squared. It turns out this one is associated with a sine substitution, this one is associated with a tangent substitution, and this one is associated with a secant substitution. Notice that they look kind of like the expressions in the form for our basic rules for arcsine, arctangent, and arcsecant. But if it's not an arcsine, an arctangent, or an arcsecant, and it's not a u-substitution, then we go to trigonometric substitution. Now, our normal formula sheet for trigonometric substitution has x's here instead of u's. But obviously we can change out the x for a u and it's still going to work. You just have to do a u substitution first. So with that in mind, when I look at this, I'm looking for one of these forms. And it's a little bit hard to see unless you remember your exponent properties. But this e to the 2x is actually a function squared. And that's because of this rule. If you take x raised to a power and you raise it to another power, remember this, all you have to do is multiply the exponents. That works for the base e as well. So this e to the 2x can actually be rewritten as an e to the x squared. Or if I let u equal e to the x, that's going to be a u squared. And since we're in the trigonometric substitution section and I've got a 1 squared minus u squared, well, now it's starting to look more like a trigonometric substitution problem. So yeah, that's how I would start this. If you're looking at this and you're stumped and you're thinking basic rules don't work, u-substitution doesn't work, like what do I do? The fact that it's in the trigonometric substitution section tells me it's got to be a 1 squared minus u squared. What must u be? And then I had to think back to my exponent properties to realize that that e to the 2x is the same thing as e to the x quantity squared. So that's what we're going to do. We're going to do a substitution first, and then we'll use a trigonometric substitution. So let's let u equal e to the 2x, or excuse me, e to the x. So that would make that a u squared there. The derivative of u in that case is e to the x, so du is e to the x dx. So I can rewrite that integral. I'll write it as the square root of 1 minus e to the x squared times an e to the x dx. And you don't have to do this step if you don't want to, but it just makes it a little bit easier and more obvious to see what that integral is in terms of u. So we'll choose u, we compute du, and then we write the integral entirely in terms of u. So that's a u, and e to the x dx, that's the same as du, so you can replace that. And now you've got this integral right here. You've got the square root of 1 minus u squared times du. And that looks like this guy right here. Now be careful, this one where you have the constant squared first minus your variable squared, that leads to a sine substitution. We'll let u equal a sine of theta. But if the variable is first, that leads to a secant substitution. In this case, we would let u equal a secant of theta. And if they're both positive, then we let u equal a times tangent of theta. But in this case, we've got that 1 squared first, so 1 squared minus u squared, so that's our a squared minus u squared. and that means we're going to make a sign substitution. Now you don't have to memorize these, but they are pretty easy to remember if you know your basic rules for arcsine, arctangent, and arcsecant, excuse me. But if you don't remember those rules, if you're not sure what to do, all of this is on the sheet that will be provided to you during the corresponding exam or quiz. So don't worry about memorizing these, just make sure that you can follow these directions if they're provided for you. And remember, those are going to be provided for you on our Blackboard site or on the website for this material. Okay, so we're making this substitution. And the first thing we do whenever we do a trig substitution is we prepare to substitute. So we're going to write everything here entirely in terms of theta. So you're going to define your u in terms of theta. You want to compute du in terms of theta. And then you want to simplify that square root of a squared minus u squared, which in this case is 1 minus u squared. That way you are not simplifying it in the integral, you're just simplifying it outside and plugging in, or excuse me, replacing the entire square root expression with whatever that is in terms of theta. So we're going to let, well, let's identify a squared first. A squared is 1, so that means a equals 1. Square root of 1 is 1. And that means that our u should be 1 times sine of theta. Then du is the derivative of sine of theta. So we have cosine of theta times d theta. And then the square root of 1 minus u squared is this. We're going to replace u with sine of theta. That was our substitution. And 1 minus sine squared theta, because of our Pythagorean identities, is cosine squared theta. And that square root function and the squaring function undo each other, and you just get cosine of theta. So we're right here now. Okay, so we've prepared to substitute. The second thing we do is we actually substitute. That was the point of preparing to substitute. So I guess we have this first step. I guess I could have just labeled it with a 1. Second step is to substitute. And of course you have to simplify and anti-differentiate. So in other words, you want to write your integral entirely in terms of theta. You want to simplify it as much as possible, and then you want to anti-differentiate. This may require the trigonometric integrals methods that we studied in the earlier section. And again, you don't have to memorize those. In my class, you've got access to that sheet that you can use as a reference during the exams or quizzes. So we've got the square root of 1 minus u squared du, and you want to write everything here in terms of theta. So according to this, the square root of 1 minus u squared turned out to be cosine of theta. So I'm just taking this and replacing that with cosine of theta. Now, a lot of students will make a mistake here and they'll forget to substitute du. They'll just say d theta there. Well, du is not the same as d theta. Remember what du was in terms of theta. If u is sine of theta, du is cosine of theta d theta. So we've got that right there. And cosine times cosine is cosine squared. Now, we do not have a basic rule for cosine squared. The answer is not cosine cubed over 3. Although it's very tempting, I would want to use the power rule there too. but I can't do that. The u-substitution wouldn't work because if u is cosine, du would be negative sine of theta d theta, and there's no negative sine of theta d theta here. There's a d theta, but the sine is not there. So we can't do that. So what I would do if I wasn't sure what to do is I would go to the trigonometric integrals sheet and look at all of the guidelines for powers of sine and cosine. They say, if the power of sine is odd and positive, do this. If the power of cosine is odd and positive, do that. If the powers of sine and cosine are both even and non-negative, use the power reducing formulas. And that's the case that we're in. I've got a power of cosine here, it's even. So we're going to use the power reducing formulas to write this in a form for which our basic rules apply. So it's even and non-negative. We want to do that. If you're saying to yourself, why can't I just replace that with 1 minus sine squared? You're right, you're absolutely right. You can replace it with 1 minus sine squared, but that won't actually help us because we don't know the integral of sine squared, just like we don't know the integral of cosine squared as it stands. Like we don't have a rule for that. So while it would be correct to replace cosine squared with 1 minus sine squared of the same angle, that's not actually going to get us to a point where we can take the antiderivative. But if we use the rule on our sheet or the guideline on our sheet that says that since the power of cosine is even and non-negative, use the power reducing formulas, or power reducing formula, we only need one because we've got cosine squared there. You'll see that when you use that power reducing formula, you will have a basic rule for everything up there. So the power reducing formula says that if you've got cosine squared of some angle, that turns out to be 1/2 of 1 plus cosine of double the angle. So whatever that angle is, you need to multiply it by 2. So I'm going to take that 1/2 outside my integral. I'm replacing cosine squared with 1/2 of 1 plus cosine of 2 times the angle. My angle was theta. So my new angle is 2 theta. And I ask myself, do I have a rule for that? I sure do. Do I have a rule for that? Absolutely. So this is going to work out just fine. So we take the antiderivative of 1 with respect to theta, and you get theta. The antiderivative of cosine is sine of the angle. Now, if that was just a theta, it would just be sine plus c, and I'd be done. But it's not just a theta. It's a constant times theta. Remember, anytime you have a constant times that variable, if you were to take the derivative, you'd have to multiply by 2 by the chain rule. When we take the antiderivative, we divide by 2 because we're undoing differentiation with antidifferentiation. So we're right here. And if you want, you can distribute at this point. Oops. So I've got 1/2 theta. 1/2 times 1/2 is 1/4. Sine of 2 theta plus c. And at this point, we typically draw a triangle and we try to write everything here entirely in terms of the original variable, which in this case, we started with x originally, but with the trig substitution, we started with u. So we're going to try to get everything here that's written in terms of theta, written in terms of u, and then at the end, we'll back substitute. Okay, so we prepared to substitute. We substituted, simplified, and we antidifferentiated. And now we want to draw a triangle. And we're going to label the sides of that triangle. In terms of the original variable, in this case, it was u for the trigonometric substitution that we're doing as part of this problem. And And the goal is to be able to write everything here entirely in terms of theta. Now, whenever you draw this triangle and you label the sides in terms of u, you want to start with your initial substitution. That is what's going to help you label those sides. And in this case, our initial substitution was u equals sine of theta. So I've got sine of theta right here equals u. And I want to write that as a fraction because if I'm thinking in terms of right triangles with right triangle trig, we always think of our trig functions as ratios. So sine of theta can be written or can be thought of as the ratio of u to 1. And remember from trig class, remember we have that mnemonic SOHCAHTOA, right? Sine is opposite over hypotenuse. So I draw a right triangle. I always put theta over here. It's just a choice, but I always make the same choice. And then if this is theta, I want the side opposite theta to have a length of u. And remember, opposite is across from theta, while the hypotenuse has a length of 1. And then by the Pythagorean theorem, this squared plus this squared equals this side squared. And if I solve for the adjacent side, let's see, let's do the arithmetic. We'll have u squared, that's 1 leg, plus the adjacent side squared equals 1 squared. Trying to get the adjacent side by itself. So I subtract the u squared from both sides, and then I take the square root. The adjacent side is the square root of 1 minus u squared. And notice that that's the a squared minus u squared that we started with in the original integral. That always happens whenever we use trigonometric substitution. Okay, so we drew our triangle, we labeled all the sides entirely in terms of u, and then we want to use this triangle and use this substitution to rewrite everything up here in terms of u as well. Now, in this case, there's actually an extra step because of this sine of 2 theta. There is no 2 theta in this triangle, there's just a theta. So I am not going to be able to find sine of 2 theta just looking at this triangle and reading off a couple of the sides. It's not going to work. But there is a trigonometric identity that relates sine of 2 theta to sine of theta and cosine of theta. So I'm going to have to make another substitution. This step is not typical. Most of the time you don't have a sine of 2 theta here. You just have trig functions in terms of theta and you can read them from the triangle. But because of the power reducing formulas, we end up with something that looks like this, and we have this little extra step. So our goal now, after we draw the triangle, is to write the antiderivative entirely in terms of u. Using the triangle as our guide. And so I have my original integral. That was that integral of 1 minus u squared du is equal to this. Well, theta we'll talk about in just a moment, but this triangle is not going to help me with sine of 2u, but we've got a trig identity. Got a double angle formula for sine. This is also on your formula sheet. I don't remember if it's on the trig integral sheet or the trig substitution sheet, but sine of 2 times an angle turns out to be 2 times sine of that angle times cosine of that angle. So I can replace this 2 or sine of 2 theta with 2 sine of theta cosine of theta. And now we're talking. Now I can write sine of theta and cosine of theta using that triangle and write it in terms of u. 2 times 1/4 is 2/4 or 1/2. And now we're here. Okay, so let's go back to our triangle. I need sine in terms of u, and turns out that sine of theta is just u over 1. Now cosine is adjacent over hypotenuse. And I'm going to do a little bit of work on this side where I'm writing all of my, I'm writing out my steps. Remember from SOHCAHTOA, cosine is adjacent over hypotenuse. So that's adjacent, that's the adjacent side of the triangle. That's the side that's next to theta, but it's not the hypotenuse, divided by the hypotenuse. So we end up with this square root of 1 minus u squared divided by 1. Which is of course just the square root of 1 minus u squared. And we're good there. And then a lot of students say, okay, but what am I supposed to do with that theta? It's actually not too bad at all. You've got sine of theta equals u. So you're just going to take that equation and solve it for theta. And if you're wondering, how do I do that? Remember, you're going to take the inverse sine of both sides. I actually don't really like that notation. I prefer to use the arc sine notation because it reminds me that it's going to give me an angle back. The inverse sine of the sine is just the angle that you started with. And I'll use arc sine because this kind of looks like 1 over sine of theta, and it's not cosecant. That's not what we mean by that at all. So I'm going to use this notation instead. So theta turns out to be arc sine of u. And we'll substitute that there as well. So we've got 1/2 times theta, which is arc sine of u, plus 1/2 times u times the square root of 1 minus u squared plus c. And we're almost done. We've finished the trigonometric substitution part. So the integral of the square root of 1 minus u squared with respect to u turns out to be 1/2 of arc sine of u, plus 1/2 of u times the square root of 1 minus u squared plus c. But that still doesn't answer the original question. Remember, the original question was this one. So you have to back substitute. You have to back substitute again. So what we did was we took this integral in terms of x and we wrote it in terms of u. Then we got here and we said, I can't do that without a trig substitution. So we did the trig substitution, which involved preparing to substitute, substituting, simplifying, and anti-differentiating, drawing a triangle, and using that labeled triangle to rewrite the answer in terms of u. That's our last step. We also had to add this trig identity in here because we had that sine of 2 theta, which occasionally comes up. And we got here, but we're not done yet until we write the answer entirely in terms of x. So the last step for us is to substitute one more time. So we call this back substituting, or if you prefer, you can just say you're going to replace u with e to the x because that's what u is. U and e to the x are the same thing. U was just something you made up at the very beginning so that we could evaluate the integral. Now it turned out that that initial substitution didn't make it possible to evaluate the integral directly, but it made it possible for us to use a trig substitution to evaluate the resulting integral. So this is our answer. We just have to replace all of the u's with e to the x. So we have 1/2 of the arc sine of u plus 1/2 of u times the square root of 1 minus u squared plus c. I'm just leaving a space for my u, and u is e to the x. Now most of the time we're going to simplify this Since x raised to a power can be simplified that way, you just multiply the exponents. We're going to multiply the exponents right there. Easy breezy. It's kind of a long problem. It did take us 2 pages because we were showing all of our work. But it's nothing you can't handle. We know how to do u-Substitution now. We know how to do trigonometric substitution. We're just putting those 2 pieces together to evaluate this integral. And if you're saying to yourself, what on earth did I just do? Remember, we're taking an antiderivative. So if you were to take the derivative of this would require the chain rule. This would require the product rule with a chain rule whenever you take the derivative of this second function here. If you do that and you simplify, guess what? You're going to get that back. The derivative of this function is this function. And that's the point. That's what we were asked to compute.